Hello everyone. Welcome back. Let me start with a curious question. Have you ever noticed how a ceiling fan takes a moment to slow down even after you switch it off? That delayed slowing down is because the current inside its coils doesn't want to change suddenly. Nature resists sudden changes in current, and the property behind this is what we call inductance. Whenever the magnetic flux linked with a coil changes with time, an EMF, an electromotive force, is induced. According to Faraday's law, the induced EMF is proportional to the rate of change of flux. Mathematically, we write this as EMF equals negative dφ by dt. Now, if the coil has capital N turns, the flux linkage is simply N times phi. And here's the essence. Inductance is the property of a circuit that quantifies how strongly it resists changes in flux, while also storing energy in the magnetic field. Think of it as the magnetic inertia of a circuit. Let's break it down further. Inductance comes in two flavors, self-inductance and mutual inductance. Self-inductance, denoted as capital L, is the ratio of flux linkage in a coil to the current in the same coil. In equation form, L equals N phi divided by I. Mutual inductance, denoted as capital M, is the flux linkage in one coil due to the current in another coil. We write it as M equals N to phi to 1 divided by I1. The C unit of inductance is the Henry, symbol H. And if you're wondering about the dimensions, they are ml squared t to the power minus 2a to the power minus 2. So the key difference? Self-inductance is like talking to yourself, while mutual inductance is like to friends sharing a secret, one's current influencing the other's flux. Now imagine two long coaxial solenoids, one placed snugly inside the other. Coil 1 has in 1 turns, coil 2 has in 2 turns, and both have length L. If a current I1 flows in coil 1, it produces a magnetic field inside it. That magnetic field is B1 equals mu naught multiplied by N1 divided by L multiplied by I1. Each turn of coil 2 experiences a flux phi to 1, which is B1 multiplied by the cross-sectional area A, that is, phi to 1 equals mu naught N1 I1 divided by L. But coil 2 has N2 turns. So the total flux linkage is N to phi to 1, which comes out to mu naught times N1 N2 divided by L multiplied by I1. As you can see in the diagram of the coaxial solenoids, the geometry ensures that flux linkage depends only on the coil dimensions, not on the actual current. From this derivation, we arrive at the neat and compact expression M equals mu naught times N1 N2 divided by L. Here, A is the common cross-sectional area of the solenoids and L is their common length. Notice that this mutual inductance does not depend on the magnitude of the current in either coil. That's the beauty of it. Mutual inductance is purely a geometrical and material property. So whenever you design a transformer or an inductor, this equation is your guiding light. Let's now look at the self-inductance of a single solenoid. Suppose the solenoid has in turns length L and cross-sectional area A. A current I flowing through it produces a magnetic field inside, B equals mu naught multiplied by N divided by L multiplied by I. The flux linked with each turn is phi equals B times A or mu naught NA I divided by L. So, the total flux linkage with all N turns is N phi equals mu naught N squared A I divided by L. And now for the punchline, self-inductance is flux linkage per unit current. That gives L equals mu naught N squared divided by L. If you check the diagram of the solenoid in your book, you'll see how increasing the number of turns makes the self-inductance rise dramatically. It's like adding more inertia to resist change. Let's put numbers to the formula with a worked example. Suppose we have two solenoids. The first has 300 turns, the second has 400 turns. The common length is 0.50 meters and the radius is 2 centimeters. We are asked to calculate the mutual inductance. We start with the formula M equals mu naught N1 N2 divided by L. The area A is pi r squared. Now substitute mu naught is 4 pi times 10 to the power minus 7. Multiply this by 300 turns, by 400 turns, by pi, by 0.02 squared. Divide the whole thing by 0.50. If you calculate carefully, you'll get M equals 6.0 times 10 to the power minus 4 Henry. Notice the final unit is Henry. Always check that in exam answers. This example shows how strongly mutual inductance depends on geometry. So to wrap it all up, inductance is the property that links current and magnetic flux. Self-inductance, capital L, equals mu naught N squared divided by L, and it depends on the solenoid's turns, area, and length. Mutual inductance, capital M, equals mu naught N1 N2 divided by L, and it represents the coupling between two coils. Both L and M oppose sudden changes in current by inducing an EMF, just as inertia resists sudden changes in motion. And why is this important? Because this principle lies at the heart of transformers, power transmission, and energy storage in magnetic fields. Without inductance, there would be no electric grids or wireless charging. I hope you now see inductance not as an abstract formula, but as a magnetic form of inertia, a hidden safeguard of stability in circuits. See you in the next session with yet another fascinating concept of physics.